good
Okay,
for
okay. So probably Holly would have introduced to you these different channels that you need to essentially define functions for. So going left to right across the page here, the axis is time. And I've shown 6 channels here. Some pulse sequences may require more channels for controlling RF switches, amplifier gates, and things like that. But these are the basic ones. These are the ones associated essentially with the NMR, the nuclear magnetic resonance of what's happening. So I'll just go through them here. At the top of the gradient coils, I think I briefly heard Holly talking about the gradient channels and how you define functions on that. So those are used for imaging. And then the next two are the RF channels. Transmit, TX is transmit, RX is receive. And then I also heard Holly mention ADC, which is analog to digital conversion. This is where we collect the data that we're going to turn into images. Um, any questions so far? Is this somewhat familiar? Okay, I'll kind of assume that it is. Um, so what we can do is think of each of these channels, not including ADC, as being current within the coils in the MRI. So think of current in the gradient X coil, the gradient Y coil, and the gradient Z coil. And in a high field MRI, like 1 Tesla or 3 Tesla, these currents can be hundreds of amps. So they're very large currents, and they take very large power amplifiers to drive. We have the coils can be the same. There might be an RF switch between them, or they could be different for transmit and receive. For transmit, you write your pulse sequence to transmit a certain pulse shape in time through that transmit coil, and then receive. Basically, the NMR generates a voltage, a very small microvolt level voltage in that receive coil. And the ADC just marks the time when you're going to collect data from that receive coil. I've divided this into times into preparation time and a measurement time. This is a quantum mechanical process, and in quantum mechanics, kind of a paradigm of measurement is you prepare your system and then to measure it, you collapse it. In MRI, we don't collapse our system. So what happens is the time of preparation and measurement will overlap. There's a fuzzy boundary between the two. So with that, what I'm going to do is I'm going to go through what happens, how to define and what happens in a basic spin echo sequence and how that leads to different contrasts. So I'm going to be talking about preparation first, and then I'm going to be talking about, and then I'll add in the gradients into the measurement discussion. That's where we actually get the data that we need to form an image. So there we go. So here's the basic spin echo sequence, and I don't have the gradient coils here, but just the transmit, receive, and the ADC. So um, this whole thing is a preparation, and the measurement happens when the ADC is open. So you can see already there's an overlap in time between when you measure and when you prepare. Although, the preparation is really these two pulses. So what happens is been told that you guys have seen the basic block equations. And so what these little pictures on the side here represent is what happens to spins in the rotating frame. So the rotating frame is basically it's a coordinate system. It's a non-inertial coordinate system that rotates at the resonant frequency. So um, the frequency of the spins in the rotating frame when they're matched with B0 is 0. And so we could just follow what happens to those spins as we tip them with various RF pulses. So the effect of RF pulses is to tip the spins in the rotating frame. So the first RF pulse we apply is a 90-degree pulse, and if you look over to pictures from 1 to 2, the 90-degree pulse flips the magnetization in the rotating frame. When the magnetization is aligned with the B0 direction, which is the Z direction, you cannot generate a signal in the receive coil. Only if the spins are in this transverse plane can you generate a signal. And as soon as you tip them in, that signal, if you were to measure it, would look like this. I guess in the rotating frame, you would just see this envelope. But if you went off frequency into, say, the lab frame, you'd see it oscillating at the resonant frequency. So what happens then is as soon as you tip that magnetization in, it immediately starts to decay. And there's two processes that cause that decay. One is the T2 decay, where the spins lose energy in processes of exchanging energy with each other, spin-spin decay. So this is the T2 decay. But on top of that, they are more directly exchanging energy with each other as ensembles, so that some spins have a higher frequency of precession and some slower. And so in the rotating frame, that causes the spins to all dephase with each other. So if you imagine that this M is a large ensemble of spins, it's composed of many smaller ensembles at different frequencies, and they dephase with each other. So this is kind of the T2 star process, and it causes the signal in the receive coil, or the voltage in the receive coil, to decay very quickly. And so to get a chance at measuring any kind of signal very early on, the experimentalists learned to apply a 180-degree pulse after a very short period of time. And this flips the spins kind of about the main spin direction, M, flips them over. And so now the spins that were lagging behind are now in front. And so they lag back into M. And the ones that were taking off away from M now will catch up with M. And after a certain amount of time, the echo time, TE, they will all come back together. And when they all come back together, everything's rephased, but that T2 decay has still happened in that time frame. And so the magnetization, this little m that you're left with to measure, is smaller than what you originally tipped over from that longitudinal direction. And you end up with a little bit less signal. So that's kind of shown here with this T2 decay envelope. And basically at the echo time, the signal comes back and you basically get this echo. So that's what happens in a basic spin echo sequence. So what we get to do is we get to play with the amount of time TE that we put in the sequence. And so you get to specify that. And so that's the first factor that's going to affect your contrast. So changing TE changes T2 contrast. So contrast, just to remind you, or if you didn't know, contrast in an image is differences in brightness. So the difference, so if we go down to the lower corner here, the difference between these two curves at any given time point is the contrast. And so with these curves here, which show T2 decay envelopes, kind of this dotted line here, and what you actually see in a spin echo sequence. So we're just concerned about the magnitude of the signal at TE here. And so at different TEs, different tissues are going to have different T2 times. And that's how we use MRI to distinguish tissues, because different tissues have these different T2 times. And if you're looking for a T2 contrast, you're going to want to keep TE short so that the differences are larger between these tissues than at a long TE time. At a long TE time, the signal will be very small, and the signals between the different tissues, the differences will be even smaller. So to get a T2 contrast, we want to keep TE short. And so all of this follows from the solution to the block equation. If you go back and look at it, with the relaxation terms, the T2 relaxation term causes this transverse magnetization to decay exponentially. So that's how we can use TE in a spin echo sequence to get T2 contrast. So then what we do is we repeat that basic sequence. So here's what we had in the previous slides, kind of compressed in time. So TE is the space here between the beginning and the middle of this ADC block when you receive your signal. And the same all the way down. It's TE is the time between the 90-degree pulse and when you measure the middle of the ADC. So we repeat that, and we repeat that at a time known as TR. So that's the repeat time. And we repeat the sequence for these three reasons, actually. One is to get a T1 contrast by changing TR. Another one is repeat the sequence without changing any parameters and then average things together. That is a standard way of increasing your signal to noise ratio through averaging, because when you average signals, the signal will increase by a factor of 2, but the noise only increases by a factor of square root 2. So you end up with more signal to noise. And also, as we'll see, we're going to use different TR instances to get different lines in K-space. And I'll talk about that as we get into the imaging. So imaging happens in Fourier transform K-space that we'll define shortly here. But focusing still on contrast, changing TR will change the T1 contrast very similarly to how changing TE changes T1 contrast. So different tissues will have different T1 times, and so they will recover back to the longitudinal state at different rates. And so when you hit these things, hit the spins with the 90-degree pulse over and over again, it depends on what your TR time is as to the magnitude of what gets actually tipped back down into that transverse plane. So in this picture here, the signal that you would get from a tissue C would end up being less than the signal that you would get from a tissue A. So tissue A would show up brighter in your image than a tissue C. So you can think of this axis here. It's the longitudinal magnetization, but it will show up in your picture as brightness from black to white, with basically you can think from 0 to 1, with 1 being white and 0 being black. That'll be digitized, of course. So it'll actually be, so if you have an 8-bit image, it'll go from 0 to 256. So these are all details that you'll need to worry about as you write actual pulse sequences. And so here's the effect of different T1 and T2 contrasts in the brain. So this kind of chart shows if you have a short TE, so basically a short TE will give you more T2 contrast. And if you have long TR, that eliminates contrast from T1. So what we have down here, yeah. So short TE, like this, shows a T1 weighted. So short in kind of MRI terms for TR, short TR is maybe half a second or less for repeat time. That means that you're going to get some T1 weighting. And if you keep TE short, things will not decay. So everything will be very much the same in contrast, and you will get no T2 contrast out there. Maybe I should flip back to the T2 because I might have explained that a little bit different. Up here, the short TE, everybody starts out at similar contrast, but as you lengthen the TE, you'll get more contrast. And I said it disappears at long TE. It does, everything disappears. But for our contrast purposes, really, short TE will keep everybody all close together in brightness. and they start to spread out the longer you make your TE. So you're going to make your TE long to get some more T2 contrast. So just to clarify something that probably didn't say quite correctly first. So this is your T1 weighted situation, short T. So to get rid of T1 weighting, you want your TRs to be very long, 2 seconds or more. And so with this, there's no T1 contrast in this. And if we keep TE really short, there's also no T2 contrast. So all that's left is the density of the protons. And so this is called proton density weighted. It's uh, it's the spins are protons, so they call it proton density. So that just basically your M0 term in your block equation, if you look at that in detail. And so the T1 terms and the T2 terms show up in the other situations. So short TE, short TR leads you to T1 weighted images because the short TE prevents the T1 or the T2 from providing any contrast, and only the T1 provides contrast. And then down here in the corners, the opposite, we make a long TR so that we don't get any T1 weighting, and a long TE so that we get T2 weighting, and really the T2 weighting dominates, and you can see that the T2 time basically of the cerebral spinal fluid here in the ventricles is the longest of all the tissues in the brain. And in this case, where you have a long T and a short TR, that gives you a mixture of different contrasts that is not useful for radiologists or interpreting, separating different tissue types. Are there any questions so far? So that's essentially the preparation part of the pulse sequence. I'll just give you guys a few seconds to maybe pitch in and ask some questions.
Yes, I have a question.
Yeah.
In this last case that you mentioned, the cerebrospinal fluids is always needed using contrast, so an additional contrast, or it's not like that. I don't have the background in the medical part, so I'm curious about that.
I didn't quite follow. Maybe say it again.
Now, I don't know if I understand right, but in this last image, bottom right, just that one, you mentioned that you are using a contrast to image the cerebrospinal fluid. Is something additional that you have to put to prepare the patient or something like that? It's I don't know about this. And
Okay. So the preparation is the preparation of the spin system. Is that kind of where you're confused? And to get the contrast, all we do is we change the TR and the TE parameters in your pulse sequence. You just change those timing parameters. Is that what you're
uh,
asking?
okay, got it. No. I thought when you mentioned this contrast, it's this liquid contrast that sometimes when you go to the doctors, they put this contrast before to take the image. So I
Right.
get confused with the terminology.
Okay, so what you're talking about is gadolinium contrast that's injected into a patient. And what that does is, if I got this right, it changes the T1 relaxation time of some of the tissues. So when you insert that contrast, this is just your basic brain the way it is, and if you inject that contrast, it will change the T1 of some tissues. In particular, if you have say a cancer tumor, the T1 contrast will go to that will affect the T1 relaxation time of that cancer tumor, and it will show up bright in an MRI image because it'll make the T1 time a lot longer. Does that make sense?
Yeah. Thank you. Got
Okay.
it.
Okay, so let's move on to imaging. And for imaging, we're going to add in those three gradient coils. Just see how much we're doing for time. Oh, we're good. So we're going to add in the three gradient coils. And what they do is they modify the main field. So the main field strength is B0 here. So, this is 1 Tesla, 3 Tesla, or, 50 millitesla for these low field MRIs. And then what they do is they cause the strength of the magnetic field to vary as you go in different directions, X, Y, or Z direction. So a thing to remember is these gradients affect the magnitude of the magnetic field. The magnetic field is always pointed in the Z direction. So that's why this K vector is here. So that's basically it. We can, I'll skip over the fact that we can turn them on all at once. But if you just focus on one of them, say if this is the X direction, if your gradient G is in an X direction, the resonant frequency, the Larmor frequency, so at 0, it will be the Larmor frequency, gamma B0. But if you go negative, the Larmor frequency, negative in X, will be less than the basic Larmor frequency for B0. And again, if you go in a positive direction, it'll be more. So what that means is the spins are precessing faster in the positive X direction and slower in the negative X direction. So if you change your transmission frequency to match the lower frequency over here or the higher frequency over here, you will excite only spins around this X coordinate here. So this is how slice selection is done. When you transmit those 90 degrees and 180 degree pulses, the slices with the gradients turned on, the slices that you will excite will depend upon your position and matching your frequency to that position. So slice selection is done by turning on the gradient and then broadcasting your RF at the frequency associated with the position that you want. Um, so this part here is that we can turn these gradients on in any combinations. So this doesn't have to be the X direction. This can be any direction in space, X, Y, Z, some combination of those. So in MRI, we can define our slice orientation however we want, just by changing basically the ratios of the currents going through the 3 different gradient coils. So then this G direction here, it becomes anything that you want to do. It's just the direction that these amplitudes of your gradients that you apply will be at. I don't know how PulseSeq is set up, but you can define things relative to the gradient direction, kind of pretending it's 0, or things with respect to the lab direction with your real X, Y, Z of the magnet coordinates. So there's generally 2 coordinate systems that you have to worry about in pulse sequence programming with slice selection and imaging. Siemens would call them logical and physical. So physical is actual GX, GY, GZ, and then logical would be with respect to this G direction, B and Z. The other factor that we need to keep in mind is the kind of pulse that you present. So the tip angle is going to be the area under the pulse curve. So that's why in the previous sequences, so we go back and take a look here. The 90-degree pulse, they're the same width, but the 180 degrees is twice as high. So the area under the 180 degrees is twice as much as the area under the 90. And the area is proportional to the tip angle. So we have some freedom to choose our tip angle with various pulse durations and various amplitudes of the pulse. So if you have a very long pulse that gives, say, a 90-degree tip angle, the amplitude is going to be small. And it turns out that the frequencies that are actually excited by your RF pulse are the Fourier transform of that pulse. So if you have a long pulse, you're going to end up exciting a very narrow frequency response, and that'll in turn give you a thin slice. So maybe, a millimeter or so. But if you have a very short pulse with a very high amplitude, That's going to give you a wide frequency response, and your slice thickness might be very large, like 10 millimeters, 15 millimeters, depending upon what your parameters are here. So a long pulse with a low amplitude, because it's a low amplitude, it's called a soft pulse. And it's a way to get a narrow frequency response or equivalently a narrow slice thickness. A hard RF pulse is, just approaching an impulse. An impulse would excite everybody. It would have, because the Fourier transform of an impulse is everything. So that's a hard RF pulse. So typically, the way we use these in a pulse sequence is if we want to excite a particular slice, we'll be using soft pulses in the presence of gradients. If we want to excite everybody, the whole volume of spins in what you're trying to image, without worrying about which slice you hit, you're going to use a hard RF pulse, and then you're gonna tip all the pulses no matter what the gradient situation is. And so there's different situations where you'll need to do that. Essentially, for the pulse sequences that we just looked at, the basic spin echo pulse sequence, you can assume soft RF pulses as you go. That'll give us some nice narrow slices, and we can be sure that all the excitations that we're doing happens only on that particular slice. There are other situations like flow imaging sequences and things like that, where you want to kind of hit everybody while you're trying to do some imaging, because you want to affect spins that are downstream in the blood from where you're imaging, and then you're going to image again to get some idea of flow. But for this, those are advanced sequences, and for this, we're just going to cover some basic spin echo ideas here. So that's how you get slices. Now, the gradients are also used to do imaging. So once a slice is excited, so in the spin echo sequence, the 90-degree pulse with a gradient on selects your slice. And then after that, we're worried about what happens in that transverse plane. So here's how the slice selection is added up here. So this basic spin echo sequence that we just talked about. We have your 90-degree pulse, your 180-degree pulse with your transmit. We're only really worried about what happens in the receive coil at the echo time. So again, this is the TE time, this very short time between these short time spacings here at the beginning. And this is the signal that we measure. When we do our transmissions in the presence of, excuse me, these gradients, then our excitation only happens on a particular slice. And so if we have a GX direction turned on, when we transmit, we're going to have slice selection in the X direction. And then you can see how the TR is used here. I have them kind of overlapping. So what happens is we're going to, if we are focused on one particular frequency, so each of these slices represents different frequencies. So slice one is say frequency one. And when we broadcast at that frequency, we're going to affect only that slice in what we're trying to image. Then we switch the frequency to a second frequency, and we're going to excite the spins in another slice two. So the TRs only apply to the slices that you're actually trying to image. And this may be a little bit more advanced for this introduction, but we're in practice, we won't do these things in order like that. We'll kind of mix them up because we want slices to not overlap each other. They will have a width and they will affect each other if they're too close. So what we want to do is we want to excite slices that are separated from each other by mixing up the slices that we select. But here I've just kind of shown slices in order. So what we need to do, so that's slice selection. And then thinking in terms of what happens on the transverse plane in that rotating frame, we're now going to add other slices. So really, to make these two things consistent, probably I should have chose Z direction as a slice direction here. So think of that as GZ for slice selection when you look at X and Y here. So X and Y really is in the plane of the um, um, of your imaging plane. It's actually different from your transverse plane if you have your gradient in an arbitrary direction. So think of this in the Z direction, and then the X and Y direction of the transverse plane corresponds to your image plane. But if you change this direction through a combination of X, Y, and Z gradients, um, then these gradients will be referred to your imaging plane. You'll have to sort that. So this is a practical thing that you'll need to sort out in your mind and sort out in your pulse sequence programming in order to get images on the excited slice. So to keep things simple though, let's pretend let's imagine this is in the Z direction, and then the X and Y direction is what you need to worry about to form an image in the XY plane that coincidentally in this case will correspond to the transverse plane. So there's two aspects that we need to worry about to get image information into that spin echo sequence, into that spin echo signal, into that NMR signal. So here's your basic spin echo sequence here. You have a 90-degree pulse, your 180-degree pulse. It echoes here, we measure that. But what we do is we encode information into this echo by applying these gradients. So this X gradient here, as I've shown it here, we'll talk about it in a bit more detail in the next slide. This X gradient will impart what's called frequency encoding into the NMR signal. So information will be put into this NMR signal by making it a mixture of a whole bunch of different frequencies that correspond to position information. In the Y direction, we will use what's known as phase encoding. And through different TRs, we'll be able to put different Y spatial information into the NMR signal through phase information. Phase and frequency, it turns out, will look the same once we write things in terms of a Fourier transform. So this kind of shows one TR of a very long sequence that's needed for imaging. And each TR, what happens is the value of the Y gradient changes. So that's what this means here. And if you were to look at each individual TR, the actual gradients that are applied would look like this. So the first TR, you'd have a large negative gradient, and then it gets less and less and less. And then you'll switch to positive gradient values, and then it'll get more and more and more with each TR. Okay, so the bottom line here is the Y gradient is used for phase encoding, and the X gradient is used for frequency encoding. So what's frequency encoding and phase encoding? Let's take a look at that. So focusing now on frequency encoding, and this is where please jump in if this gets a little crazy, because there's a lot here. So in the rotating frame, the temporal frequency. So rotating frame corresponds to in the radio language superheterodyne detection. So you detect at a particular frequency. So in a radio, right? So an AM station will broadcast at so many kilohertz. And then when your radio actually subtracts that kilohertz off, and so what you're left with is just small changes in the frequency that correspond to voice and music. So that's what happens here. In the rotating frame, the frequencies So there will be no precession in the rotating frame if there's no gradient applied. That's at B0, the resonant frequency. And then but the frequency, if you apply a gradient, the frequency will depend on your spatial position X. So this is a temporal frequency. This is so many hertz, so many cycles per second at a given spatial location. And so what we want to do is this is the trick that got, Lauterbur and Mansfield their Nobel Prizes. They uh, figured out how to interpret this temporal frequency, this frequency in time, as a spatial frequency, a frequency across space. So they came up with the scheme that we're going through here, this frequency and phase encoding. They came up with this scheme. It's called spin warp, by the way. People don't use that term so much anymore, but the idea was to convert this temporal frequency into a spatial frequency so that you could then use a Fourier transform to get your image. So given that this is the temporal frequency, the actual signal that we're going to measure with that AZC on that receive coil looks like this. So it looks kind of like a Fourier transform, but this is the actual frequency that you're seeing. So we have to integrate over the whole thing because the frequency is different at each different spatial position. So P here, basically think of that as X for this, but we're going to add in the Y. That's going to change depending upon your spatial position. So if we do go explicitly to X and Y, the signal is going to look like this. I'm going to stop here and see if there are any questions. So either you're getting it or you're completely overwhelmed.
Hello, can I ask?
Yeah,
Yeah, do you mind going on that slide whereby you're talking about a long RF frequency, sorry, pulse excites a narrow slice, and then whatever is going to be imaged is dependent on the Fourier transform of your pulse. I didn't understand that part of the Fourier transform of your pulse. Yeah,
right.
that's part.
Okay. So this Fourier transform is completely different from the Fourier transform that we're going to talk about for imaging. And so what happens is the frequency component of an RF pulse, just by virtue of, I don't know, math, essentially, any function is going to have a certain frequency component. And it is those frequencies in that pulse that will end up affecting your spins. Okay, so this is kind of a basic Fourier transform property of any functions. Doesn't matter what you're talking about. If you have a function that has a long, time, its Fourier transform is going to have short number of frequencies. This is basically the uncertainty principle. You'll see it in quantum mechanics. So if we go from a position space to a momentum space, a large delta in position will lead to a small delta in momentum. So momentum is frequency in physics, in quantum physics. So basically, if you want to understand which frequencies are affected by your RF pulse, you have to know what the resonant frequencies of your spins are that it's going after. So this a long pulse will only have a few frequencies in it, whereas a short one will have a lot. So you'll end up affecting more frequencies here than here. Does that clarify it at all?
Yes, it tries to.
Okay,
Thanks.
yeah. I mean, you have to think about that. You really have to become comfortable with Fourier transform to become proficient in MRI. There's no way around it because it shows up everywhere. So that's how it shows up with just pulse sequences and what it excites. And here it shows up because we're doing a trick to turn temporal frequency into spatial frequency. So anyway, so this is the signal that you end up with. It arises because we deliberately make the resonant frequency of everybody different depending upon their X position. And then we put them all together. And this looks like a mess, but the Fourier transform allows us to undo that mess. So the trick here, this is the Nobel Prize kind winning equation here, is we convert this temporal frequency here in time to this spatial frequency using this association. Okay, so then the spatial frequency now depends on time. It's not just a regular temporal frequency anymore dependent on X. It's a spatial frequency that depends on time. So we swap the roles of space and time doing this. And that leads us to a signal that looks like this. And this is important because now this looks like a Fourier transform with, forgetting about the t at each moment in time. We have a different signal. So at each moment in time, we have a different kx value. And we can plot that this way. So for each different time, we have a different kx value. So that's the frequency encoding. So we get different kx values. And this is the gradient kind of form that will lead to those kind of different positions. So we need a negative one at the first. So your signal always starts out 0 in k-space. And then we need this negative trajectory done actually before you do any ADC. And then with this on when you're collecting your ADC. So I think that's here. So the gradient is on at the same time as the ADC. And that leads to your different k-space. So as you sample your signal in time along here, each one of those signals at these different times represents one k-space position. So that's the ADC part of it. Sorry. You convert, so you sample with your analog to digital conversion one number at every point in time. That's what your ADC gives you. It gives you, and at the end of the day, a bunch of numbers that you're going to do Fourier calculations on to get your image. So this is how you, after you digitize that signal, that wavy signal, you end up with different values, and those values represent values of the Fourier transform of the image at these different kx points. One thing, is probably a little bit much to gather in 5 minutes here, but this is negative here. And when you see it here, it's positive here. And that's because the 180-degree pulse is a general feature, moves you from one side of k-space to the other. So that's the effect of a 180-degree pulse if you're not in the middle of k-space. So that's a detail. I would say at this point, just kind of accept that you need that. But the take-home thing, message here that you should be really trying to understand is that as you sample the signal at different points in time, you end up with the value of the image that you're after at different points in this temporal frequency k-space. So that's our frequency encoding. That gives you X. But what about the Y? An image is two-dimensional. We need to get the Y. So yeah, so I kind of didn't talk about this, but I said this looks like a Fourier transform. This is how to really make it look like a Fourier transform in one dimension. So the signal is the Fourier transform at a particular kx position of H, which is kind of the image that we're after. But here, this is exact.
May I have do a question?
Okay, sure.
Sure. Just looking in the diagram in the previous slide, I'm wondering there when you are sampling with the ADC, it's needed to really sample the full RF signal, or it will be enough to just get the envelope of that signal? And then the other question is, what is going to happen if you don't really sample really well? So you are not recovering the full signal, and then it's not well sampled. So what is going to be the effect of that?
Okay. So first of all, yeah, this is kind of a schematic. The signal that we're actually going to receive, I mean, after superheterodyne detection, is going to be, it'll be essentially the envelope of this if this is the Larmor frequency. But in the rotating frame, all you're going to see is the envelope. So really, what you're going to see is a shape here that corresponds to the Fourier transform of your object in the x direction.
Okay.
Yeah. And so you do
So,
have
so,
to,
so it's like kind of it's modulated. It's like it was modulated there, something like that.
yes. So everything when you think about things in the rotating frame, you're thinking about everything's already modulated. The Larmor frequency is modulated out of any data that you're collecting. Does that make
Okay.
sense?
Yeah.
And
Yeah.
then your other question was about sampling. So I mean, I've never seen it, but you could do everything in an analog fashion. But these days, everybody digitizes your signal, and you need to get enough samples of your signal in order to get proper image reconstruction. So we're going to have in the next few slides, we're going to talk about aliasing and field of view, and so the sampling frequency that you do will affect those two parameters.
Uh, yeah. Yeah.
Okay.
My question was going in that direction. Okay.
Okay. Okay. There's a lot of moving parts here. So, so we have a Fourier transform of the image that we're interested, but really only a projection of that image, right? So like kind of an X-ray version of that image in one direction. So we need to get it, so that's frequency encoding. And in order to get in the Y direction, we use this process of phase encoding. So for phase encoding, as we showed in this previous slide, we have a different value of Y for each TR. So each TR is going to give us basically it's going to give us a different value of the KY that we need. Okay, so the KY is going to depend upon, and I have GY times tau time duration. That's a little bit different from what I shown here. So here I've shown that the tau duration is the same for everybody, but I changed GY. In this equation, it's the other way around. I have GY fixed and the tau is changed. Again, your KY position is the area under these guys. So the area here is actually going to translate to your KY position. So it doesn't matter how you do it, whether you change the amplitude and leave the time fixed or change the time and keep the time fixed and change, sorry, the other way around. Keep the value of magnitude fixed and change the time. Either way, you're going to get the same KY position. So it's just kind of I guess, a mathematical thing that this is a little bit cleaner to write out this way. In any case, so this shows the integral, which gives you your position in Kx and Ky. So in general, um, this happens during the ADC time, this integral. And so the more so when you start out with your first signal samples, they'll be at the beginning of Kx, and then as you increase time more and more for your different samples, you'll get Kx samples across in the Kx direction. And then here, yeah, you can change this during acquisition, but you can think of this as simply being the area under each of those blocks. These symbols don't correspond exactly to that situation. But if you change the area under those curves so that this ends up being the KY position that you want to get, you'll get different values in the KY. And so what that means is in the KX space, as you have KY turned on, you're going to frequency encode along this direction. So basically, the KY phase encoding prepares your spins up here to be in a particular KY position. And then as you measure it with frequency encoding, you measure sample points along the KX direction. So with each TR, you're going to be at a different KY position. Okay, so you start off with a large area under that KY gradient. That'll put you up here. You reduce the area either by reducing the time of the pulse or the magnitude. Generally, we do reduce the magnitude of that pulse to keep your pulse sequence simple. And you get a different line in K space. The KY changes, but each time you collect your signal, you're getting the same KX values. And so you can say that if we repeat the acquisition M times, changing the KY gradient each time, we're going to get M lines in K space. And then depending on your ADC setting, you're going to get N samples each time you collect a signal with that ADC. So if we label each KY acquisition, each TR with a little m, so there's capital M of them. So we have M signals, capital M signals altogether, indexed by this little m. And then each of our sample points here will have capital N of them, and we'll index that by N. So each sample for each signal M looks like this. And this is exactly the Fourier transform of the image, this rho xy that we're after. So we need, if we collect all this data, apply a Fourier transform, say through a fast Fourier transform, FFT, whatever, take it out of your canned packages that might come with Python or PulseSeq, I don't know what's in it. You apply that Fourier transform, and you end up with this image or an approximation of that image. And we'll talk about that approximation here in a minute. But that's how you get the image. So in this setup, each of these, this is the constant amplitude of GX gradient, and then we vary the amplitude of the GY gradient. So that's a typical way of doing an imaging pulse sequence. These are the explicit values of KX and KY that and they're shown explicitly in here. So in terms of KX and KY, after doing this Nobel Prize winning transformation from time to position, we end up with our signals that look like this. So for signal N and M corresponding to, a spot on this diagram, we have this particular value of the Fourier transform. And if we that's what we have. And so then we can use the Fourier transform to convert from KX and KY to X and Y. And then we have a picture. Again, questions at this point? Usually this is where most students are overwhelmed.
I have a question.
Yeah.
I have seen in some other textbooks and practices that the sample should also focus on the origin of the K-space. And in this illustration, you're avoiding the center. So I'm wondering whether there is a particular opinion of yours that basically can provide any insight of why we should sample the center of the K-space, or why we shouldn't, or why it could be avoided without any negative repercussion.
In fact, you should center the origin of K-space because that's where you're going to get the most signal. So this particular scheme I have here is kind of mathematically convenient one. When you do Fourier transform, it avoids problems at the ends of the frequencies. So there's two issues here. One is the application of the fast Fourier transform. What happens is the signal is periodic, and I'm going to talk about that in a minute. So when you do a fast Fourier transform, after it's sorted, the negative frequency is going to be same information as a positive frequency at some point. So you have to be careful about how you line up things when you have the zero. You have to be less careful when you avoid it. But in real life, you're gonna want to sample. You're gonna want to sample the center of K-space because that's where you get most signal. That defines your contrast most cleanly. But you're gonna have to be careful when you apply numerical Fourier transforms. So I'm not going to talk about the details of those numerical Fourier transforms. That's more kind of in the programming math realm than really in MRI. Does that clarify it a little bit?
Yeah, thank you.
Okay. Okay, so we have this data and we're going to Fourier transform it. So what does that mean? So here's how we actually Fourier transform it. A real Fourier transform would be an integral, but we only have discrete data. So we're going to do a sum. We're going to do an approximation of that Fourier transform integral, and it looks like this. So what we have now mathematically is a Fourier series. Fourier series in mathematics always lead to a periodic function. Okay, so that's key to understanding aliasing. The function that this is going to define is going to be periodic. And so the other thing is so samples in a sum here. The real consequence is the sum leads to a periodic function. And the other thing is the extent that we go out in Kx and Ky. I mean, to get a exact Fourier transform, we have to go from minus infinity to plus infinity for Kx and Ky. We can't do that. We're limited in how far out we can go. So that leads to limitations in our resolution that we'll talk about. So I haven't so rho is what the image came from, the actual head. But the image that we get is an approximation. So that's why I use P rho. So it's an approximation of what we get. And that approximation is it's a limited field of view and limited resolution. So those are the approximations that happen when you do this. I'm a math guy, so a lot of my software has this equation in it explicitly. But most people, when they're doing image reconstruction with MRI pulse sequences, will be using a fast Fourier transform. A fast Fourier transform gives you actually a quick way of doing this particular sum by shuffling things around. There's nice, cool mathematical reasons why that works, but the bottom line is it gives you this particular sum, and you have to worry about shuffling frequencies and things like that. A lot of CAN packages that you would get will handle all of those details for you without you having to worry about them. Okay, so this is how we get from the signals. So remember, just to recap, remember we got the M different signals from changing the GY gradient, different values of GY gradient with each TR. We got the N different points through our ADC sampling with each one of those TRs. So we have M times N. Usually we set these to be equal to each other, say M and N equal to 256 each to get a 256 by 256 image. A fast Fourier transform will give you the same number of image pixel points as sample points that you put into them. So if you put in 256 by 256 data set, fast Fourier transform, it gives you a 256 by 256 pixel image. There's tricks. You may have heard of zero filling and things like that. That essentially changes the M and N values. But that's kind of more advanced signal processing technique than the basic things here. Okay, so let's look at the consequences of the fact that we're using a sum and that the extent of Kx and Ky is limited. So let's focus on number one. So we only sample the the spatial frequencies of the image that we're interested in within a very limited boundary, right? Because we only have so much time to acquire our signal. And in real life, as you get further and further out on the edge of the K-space, the signal is small. And there's noise limits to how far out in K-space you can go because of that. But if we just think of if we could get all of the data in this little space, we can't, but if we could, then this would define a function. So that this would define a function in K-space where we collect our data. So we imagine a function that's equal to 1 where it's shaded and 0 outside of that. So let's call that phi hat. It's equal to 1 in the gray space and 0 outside of that. If we Fourier transform that, we get what's known as the point spread function. So if you go back to basic mathematics of Fourier transform, there's a theorem that says if you multiply on the Fourier transform side two functions, you end up with a convolution of the Fourier transform of each of those functions after you Fourier transform. So this is in K-space. You can think of your K-space data as being the real Fourier transform, not the approximate, the real Fourier transform of the image multiplied by this function. So we only have values of the Fourier transform inside the gray area. We don't have any information about the Fourier transform outside of that. So mathematically, we're multiplying them. And then after we Fourier transform this whole thing, which is what we actually do in real life, we have this convolution. And so what this convolution represents is if we had a perfect image, this phi would be a delta function, and then we'd have exactly rho, but it's spread out. So this will be some function. So it's kind of an exercise that I give in my class here when we have, the whole term. Calculate the Fourier transform of this guy. You'll find out that it's a sinc function, a sine x over x function. It's kind of, peaks in the middle and then tapers off with waves on each side. So an individual point in the original image gets smeared out by that sinc function, and that's what this represents. Now, in real life, we don't have all of this data. We only have samples of this data, right? We only got these guys. So it is possible if we define delta functions at each of these guys, we can Fourier transform that. And that's easy to calculate. That gives you this function. So this is the real point spread function of your image. So your resolution is limited by this. So to increase your resolution, you need to go to higher values of kx and ky. You need to get out here. The diameter of this K-space where you collect defines your resolution. So larger K-space diameter gives higher image resolution. That's the take-home message. And the resolution itself is the full width half maximum of that point spread function. So if you imagine that sinc function and the width of that sinc function, sine x over x, plotted it, I'm sure you've probably seen that many times. You look at that function and the full width half maximum of that is actually the resolution that you get. And it turns out if we collect M and N samples and reconstruct an M by N image, that resolution is basically equal to the pixel size of your image, right? So you take Vx and Vy are going to be the field of view in the X and Y direction of your image. I'll talk about that in the next slide. And you divide by the number of samples you have. That's your pixel size, and that corresponds actually to the resolution. Once you start messing with the reconstruction algorithms, you're never going to change that resolution. You might get images that have more pixels or things like that, but a lot of people call this the physical resolution of your image. This is all the information that you have, okay? So that's the resolution side of using this formula. The other side is it is a sum. So that leads to periodic functions. So usually we just calculate everything within the field of view. So here's your field of view, Vx and Vy. And if your object is smaller than your field of view, you're good. We just, do one at a time. But if you were to calculate values of that image outside of the field of view, so if you pick values here for X and Y that were actually outside of the field of view, anything that you wanted, you would actually end up making these kinds of pictures. I think they're kind of cool when you do that, but you can do these kinds of tricks and show explicitly that sum is really a periodic function. And so the consequence of that is it's going to be periodic function no matter what you do. So if your case-based sampling, and this is the formula for the field of view, if your case-based sampling is too wide, your field of view goes down. This is again the uncertainty principle. It shows up everywhere every time you use a Fourier transform. So if your delta K is too large, if you don't get enough samples, getting back to that earlier question, if you don't get enough samples and your time between your samples is too far, your delta K is going to be big, your field of view is going to be small, and you could end up with a situation like this where your image is folded because it's gonna be periodic. And how does that show up being periodic? You see stuff that should be out here is outside of the field of view. It has to be in the field of view. That equation is going to make it periodic and it's going to force it down here. And that's where it's going to show up. So that's the source of aliasing. So to avoid aliasing, you must have your field of view larger than your object, which means you have to have your delta K small enough to avoid that. And we're done. That's the basics of pulse sequences, what they do to you, and at the end of the day, you're going to go back to your pulse sequence programming and start putting things in here, and the things that you put in here are going to be these RF pulses, and ultimately you're going to do a pulse sequence that looks like this. Okay.
I have another question, please.
Yeah.
Regarding the aliasing that you were mentioning, I was wondering, this make a lot of sense when we are talking about the brain, for example, because the brain, well, is going to be isolated and we have the full object there. But what happens if we are scanning just a part of the organ? Let's say that the field of view is just a few centimeters and we want to just scan, let's say, something that is not isolated. I mean, that in which the object is larger than the field of view.
So there's a number of ways to do that, but basically, let's say you're interested in imaging the heart, right? So the heart's smaller. You cannot avoid aliasing. If you're going to image the heart, you have to image the whole cross section of the body. So that your field of view has to be that much larger. So your heart's going to be this little thing in the middle of this larger section. And the only way to get around that is to improve your resolution so that you can actually just look at the heart in more detail. And so to improve the resolution, you got to go further in K-space. Another way around that is to try and excite only that small region. Then your field of view is not defined by the object, but it's defined by what you excite. So there's
So basically we would be doing a slice selection, let's say voxel excitation or something like that.
So everything that we talk about here, this is all within one excited slice, right? So what happens in the other slices doesn't affect anything that we're talking about. Only your field of view is only in that slice, and you only have to worry about where the object is in that particular slice.
All right. But in any case, aliasing could also be happening because of the imprecisions and imperfections of hardware, I guess.
Not really. Aliasing happens 100% because you're not sampling enough.
Right, so it's unavoidable, basically.
Yeah, you have to get your field of view large enough. It is unavoidable. Yes, absolutely.
Thank you.
Yeah.
All right, so thank you so much, Professor Golden. So
Okay.
we are very happy to have you, and guys, you are lucky to to get a lecture from him, and that is really an honor.